Howdy. In this video, we're going to go over on how to perform the reduction of a simple distributed loading. But what is a distributed loading, or how does it look like? Well, if we look at the book, some of your examples are going to look something like this. Here we have a cantilever beam, right, that is attached to a wall at point A. But now look at this loading over here. So instead of having single point loads, which we know how to deal with perfectly by now, instead what we have is a bunch of arrows pointing down, right? This bunch of arrows pointing down is what we refer to as distributed loading, because the loading is distributed along the axis of this beam over here. Take a look at the units over here and the values. So this is saying that at this point, there's a load of 100 pounds per foot being applied here to the beam. So again, it's a force per a distance, right? But this is not constant. This load is dropping, or distributed loading is dropping to this point over here where we have only 50 pounds per foot. So that's what distributed loading look like. It's gonna be a force per a distance. And so for today, we'll show you how to determine the magnitude and location of the equivalent resultant force. What we want to do is replace this distributed loading with a single force that's going to point down on this beam, right? So we'll determine what the magnitude of the force is supposed to be and where we put it, such that that resultant force is going to produce the same external effects on this body. So how is it that we can end up with loading such as 100 pounds per foot, or force per distance? Let's take a look at this other graphic over here. This is meant to depict a sign over here. The sign is 1 meter tall over here and it's 2 meters wide. And then let's say the sign is standing outside and there's a wind, right? The wind is blowing and it's applying a 10 Pascal pressure on that sign. So again, this is due to the wind blowing. And so if I ask you, okay, we know how much pressure the wind is exerting on the sign, but in statics, we always deal with forces, not with pressure, right? So how much force is that pressure gonna put on that sign? Well, it's kind of easy to calculate for this case, because they tell us that the pressure is 10 pascals. And if you remember from physics, that a Pascal is nothing but a Newton per meter squared. So what this is saying is that every meter squared of area is going to receive a force of 10 newtons. 10 newtons per every meter. So how much area do we have? So we have 1 meter high, 2 meters wide. So 1 times 2 is 2. So we have a cross-sectional area of 2 square meters. And if we say, look, the pressure is putting 10 newtons per each meter because we have 2 meters, right? The total force in here is going to be 20 pascals. We can solve this problem also with the pressure equation. So we know that the pressure is just the force divided by the area. If we want to figure out how much force is the sign feeling or being exerted on the sign, we can solve for F over here. And F is just going to be P times A, or the pressure times the area. Again, in this case, we said the pressure was 10 newtons per meter squared, or pascals. The area was 1 by 2, or 2 square meters, right? Here meters cancels with meters, and 10 times 2 is 20 newtons. And that's the force that's being exerted at the sign. Now if I ask you, okay, now I know how much force is being exerted at the sign. If I want to use, right, just a single resultant force, which is this guy, where do you think we should put it on the sign? On the lower corner, top corner, over here this back corner. So where should we put it? right? Instinctively, you might say, well, we'll put it right down the middle. And that's a correct answer. Why? Because this pressure, if we want to reduce this distributed loading, which in this case is the pressure acting on the sign, the best way to choose it or to put it into is going to be the centroid of this area. Now this still doesn't explain how we can get into this type of loading, right? Where we have force per distance, which we call distributed loading. So to answer that question, we got to look at this example, which is in 3D right now, and look at it as a 2D example. So a lot of the times we'll take a 3D problem and we'll represent it with a two-dimensional model. So here what we'll do is, again, we had a pressure acting over an area, but now we're looking at just in 2 dimensions. So let's say if we're looking here from the z-axis this way, all I will see is the loading going in this direction, right? So I can't capture the width of the sign, that's 2 meters, in this representation, but we can take care of that with a very simple trick. So if we take this pressure, again, which is 10 megapascals or 10 Newton per meter, so I'm gonna take it over here, 10 Newton per meter squared, sorry. And because the sign has its height, it's constant and it's not varying, right? So this dimension is the same. I can go ahead and multiply times the width over here, times 2 meters. And what I get is 10 times 2 is 20 newtons. And then one of the meters from the top is going to cancel with one from the bottom. And we have something that looks like 20 newtons per meter, right? So another way to look at this is anytime you see a distributed loading of a force per a distance, right? Just remember that this probably came from a pressure, right? And we already multiplied by this width over here to simplify and just simply look at this problem in a 2D. So now to solve this problem here with the sign, right? This height still hasn't changed. It's still 1 meter. And if we ask you this question again, determine the magnitude and location of the equivalent resultant force, what will we do? Well, now what we know from this problem is that this loading has a magnitude of 20 newtons per meter, right? Since we have 1 meter, right, it makes sense that the resultant force is going to be 20 newtons. To calculate the resultant force when we have a distributed loading, the resultant force is just going to be the area. Now the area is going to have some funky numbers again, because what is it that we're multiplying? It says like we're getting the purple area here, right? So this, you can think of it as having a base here, the length of this arrow. Remember, the length of the arrows usually they represent the magnitude of the loading, right? So here the base area is base times the height, where the base over here has units of 20 Newton per meter, right? The height has a unit of a magnitude of 1 and a unit of meter. So when we multiply these two together, 20 times 1, right, gives you the 20, the meter from the bottom cancels with this meter, and we end up with this resultant force. So again, the resultant force is going to be just the area of the curve. In a little bit, we'll go through this example so we get more practice. So the resultant force is just the area. The next thing we need to worry about is where do we put that force? Like on this sign, where do we put it? Your intuition tells us we want to put this force right at the middle. And really what that means is that the location is going to be at the centroid of the area. So we're back at the problem where we want to determine the magnitude, magnitude and location of the equivalent resultant force. Right now we know that the magnitude is equal to the area of the distributed loading, and the location right is going to be at the centroid. So the first step in solving these types of problems is going to be looking at your distributed loading over here, right? And again, because what we're trying to do is calculate areas, the best approach is going to be to divide this into simple shapes so that it's easy to calculate the areas, because I, for one, don't remember how to calculate this area over here. But what I do know how to do is calculate the area of see if I put a straight line over here. I know how to calculate the area of a triangle and the area of this rectangle over here. So I'll go ahead and label the areas. This top one, I'll call it number 1, and this one, the rectangle, I'll call it number 2. So let me go ahead and summarize the steps that we'll be taking over here. So the steps are: 1, divide into simple shapes, which is what I just did. Step 2 is going to be calculate the area of shapes. So in this example, we have 2 shapes. Number 1, which is the triangle that looks like this, right? And shape number 2, which is the rectangle. So do you remember the area of a triangle, right? It's 1/2 base times height, right? So we have 1/2. What is the base? Well, the base of the triangle is 3 feet. And then what is the height of the triangle? Well, let's take a look at this, right? At this point over here, they're telling us that the magnitude is 100 pounds per feet. So you can think this as being 100 pound per feet tall. And then the triangle slopes down all the way over here. At this point, this height is 50, right? But that's the height for the rectangle. So if I wanted to figure out what is the height of the triangle, so 100 minus 50 gives me 50. So this right here is 50. So let me write the units the correct way so I don't throw you off. So we said the base was 3 feet and the height is 50 pounds per feet, right? What happens when we multiply this feet is going to cancel with this one, and at the end of the day, this area over here is going to have units of pounds. So 1/2 of 50 is 25, multiply times 3 is 75. So what this means is that this distributed load that has the form of this triangle is putting 75 pounds of force on this beam. So now let's calculate the area of the rectangle. The area of the rectangle is just base times height. So the base of the rectangle is 3 feet. What is the height of the rectangle? Well, the height, we grab it from this point over here, which is 50 pounds per foot. And so what we have is 3 times 50, which is 150, and it's going to have units of pounds. So now that we have calculated the areas, the next step is going to be to calculate the location, right? Where that force from the distributed loading for the triangle and the rectangle is going to act upon on the beam. So step 3 is find the location. Right? To do this, it's going to be best just to do a free body diagram. So if I go something like this, let me go further down. So what I'll do is a free body diagram of this cantilever beam. Here's our point A. Again, I have the loading, the resultant load from the triangular shaped distributed load. It's 75 pounds, right? When we look at these arrows, the arrows are pointing down, right? So I know I need to put a force of 75 pounds. The question is, where does it go? And if you remember our previous example, we said, hey, the location is right at the centroid of the area. So now what I need to do is locate the centroid of the triangular area. So if you remember in class, we said that the centroid along here, the base for a right triangle is going to be 1/3 of the distance from the right angle, right? Since the base of this triangle is 3, right? The centroid for the triangle is going to be roughly right here or a foot away from this point. So again, here's where the right angle is. If I move 1 foot this way, at that point I can put this 75-pound load. Now, it's going to be to our advantage to locate that point relative to this point A over here, right? So from A to the start of the triangle is 3 feet, right? And then we need to move 1 foot so that we are at the center of the triangle, right? So 3 plus 1, this is going to tell us that this guy is at 4 feet relative to point A. Now, let's find the location for the rectangular distributed loading here, this area 2, right? So where is the centroid of the rectangle? Right down the center or the middle. If the base is 3, right, this is going to be half of 3 or 1.5 feet, right, from the start over here. So I can put another arrow. Let me change the color. Hopefully you'll see this as purple. But again, 1.5 feet. And then this guy is the area of the rectangle, 150 pounds. Now let's go ahead and locate that point relative to point A. So I'm going to go here to this guy. Right, to go from A to this point, this is 3 plus half of 3 or 1.5 to get to the centroid. So 3 plus 1.5 is going to be 4.5 feet. Right? And so now we simplified each of the distributed loadings, the rectangular one, 150, and the triangular one. We have the magnitude of the two and the location of each of the two forces. However, what we need to do is we need to replace these two forces with a single resultant force. Remember, this is what we covered in the previous lecture called simplification of a force and coupled system. Again, so what we want to do now is simplify these two forces into a single resultant force, and we want its location. However, we can't get to that state directly. Instead, what we need to do is we need to replace these two forces with a single resultant force and couple moment at point A. So I'll do another free body diagram over here. This is the beam. This is A. And now we want a single resultant force and couple moment acting at A. Do you remember how to calculate the resultant of a force? It's just the sum of the forces, right? So the resultant force is just the sum of the forces. In this case, we have two. We have 75 and 150, right? Normally, when we're calculating the resultant, we would have to worry about summing forces in the x and summing forces in the y. In this problem, all we have is forces in the y. So by just summing all the forces in the y, we essentially computed the resultant. Again, there's no forces in the x. So what we have is we have 75, and then the other force is 150. So when I add the two together, 150 plus 75 is going to be 225. It has the units of pounds, and again, because these two forces are pointing down, right, that resultant is going to point down. So what this means is I can replace these two forces with this single resultant force of 225 pounds at point A. However, right, it's not just finding that resultant, because if you remember from the previous videos, we say if we move a force, right, we cannot just move a force to a point that is not in its line of action, because if I have this and I have the 75-pound force and the 150, both of these are trying to, relative to point A, right, besides trying to move this body down, they're also trying to make it rotate, in this case clockwise. So I can't just say, oh, I found the resultant over here. I also need to capture that tendency to rotate. Right? Do you remember the formula for calculating the resultant couple moment? So the resultant couple moment, in this case about point A, is just the sum of the moments about point A plus any couple moments that exist in the free body diagram. In this case, we have no couple moments. We just had some distributed loading and no couple moments, no equal and opposite forces or nothing that looks like this. So in this case, this is going to go to 0. And again, all we have to worry about is the moment that each of the forces can cause about point. So this guy, right, we have two. The first one is going to be the 75-pound force, right? The distance is 4 feet, right? And as we're summing the moments, remember we always say if it's counterclockwise, it's positive. In this case, if I'm at point A, right, we put our right hand there, I go point to the force, the 75 curls down, so that means it curls clockwise, right? Or if you're doing this on a sheet of paper, right, this would be down, that's a negative moment, so this is negative right here. The 150 is going to have the same direction, so it's also going to be a negative. So minus the force, 150 pounds, times the distance to the 150, which is 4.5 feet. Right, we have no other forces acting. Again, we have no couple moments, so the sum of these two moments is going to give us a resultant couple. Let's go ahead and calculate it. So we're going to type in the calculator minus 75 times 4 minus 150 times 4.5. And this gives minus 975. Right? What are the units? Pounds, feet. This being negative means that we have a clockwise moment. So we have a clockwise moment of 975 pound-feet. However, we're still not done, right? Again, the question was to determine the magnitude and location of the equivalent resultant force. Right now, we've simplified everything to a resultant force in couple moment at A but we need to now further simplify to just a resultant force. You remember how we do that? We do the free body diagram. Right, we're looking for that equivalent system that is going to capture both the 225 resultant force and this tendency to rotate. We can further simplify by taking this resultant force, and if I move this resultant force just the right distance and in the right direction, I can recreate this tendency to rotate about this point A over here. So the question is going to be, first, which direction should I move this resultant force? If I go this way, right, not only is it off the body, but if the force is here to our left and is pushing down, it's going to create a positive rotation. Here we want a negative or a clockwise rotation. So it makes sense that I need to move this force down here to the right so that when it pivots at point A, and if I push down, it'll rotate clockwise. So we're looking here for the force. Again, we know is 225 pounds. What we're after is, what is the distance? And the answer is rather simple, right? Why? Because we already calculated the resultant moment at A. Now remember we said, look, a moment is just a force times a distance, and we can solve for this distance, right, by taking our moment and then dividing by the force. We also said that we're not going to use just any moment. Now the moment that we're trying to replace, right, is the resultant couple moment at A. So resultant moment at A. And if we divide by the resultant force, this Fr of 225, we should be able to solve for that distance real quickly. So again, the resultant moment is 975. Oops. Right, and it has units of pound feet. Divided by the resultant force, which is 225 pounds. Here, pounds cancels with the pounds. And our answer is just going to be in feet. So we take 975 divided by 225, and we get a distance of 4.333. So this D here, this distance is 4.33 feet. Does it make sense that this resultant force is 4.33? Let's take a look at this figure over here. So we had a 75-pound force at 4 feet, 150 pounds at 4.5. We're replacing this tool with a single one going down. It's 225, right? And it only makes sense that it's in between these two forces. It would be pointless if we calculated a D and it gave us 10 or 12 feet or minus a number over here, right? So the end result is somewhere here. So it makes perfect sense that our distance has to be 4.33. So again, now we've determined the magnitude and location of the equivalent resultant force. Again, that resultant force is 225, right? And the location is 4.33 meters to the right, or point A over here. So to complete the steps here that I took, right? First, we divided the distributed load into simple shapes. We calculated the area of each of the simple shapes. We found the location of the centroid for each of the simple shapes. Then what we did, step 4, we simplified into a force and couple at some point. In this case, we chose point A. And then the last step, we further simplified that force and couple system into just a force some distance away from a point A. Again, that was going to capture that tendency to rotate. So if someone were to ask you, what is the end effect of this distributed load? that starts off over here with a magnitude of 100 pounds per foot and decreases to 50 pounds per foot at the end of the beam. What is it trying to do? Well, it's the same thing as applying a force of 225 here at a distance 4.333. Another important point to mention is that all of these free body diagrams are what we call equivalent force systems. Although they don't look like it, right? There's distributed load, 2-point loads, a single resultant in a couple moment, or just a force at some distance from a point. Although they don't look similar, right? If we model these as this beam as a rigid body like we do in statics, they all have the same effects on the body. They produce the same thing, and so we call them equivalent force system. All of this, 1, 2, 3, 4. Also, hopefully you can appreciate the simplicity instead of having all these distributed loads of just having one force and knowing some distance. Also knowing that that force is going to create a tendency to rotate, which is our resulting couple moment at point A. So I hope you found this video useful. As always, if you found any mistakes on the calculations that I did over here, please let everybody know in the comments. Otherwise, we'll see you on the next one.